Okay, so today we are going to start looking at how we interpret and create graphs based on different situations. So we have been looking at functions that are linear, right? And we've just been looking at graphs that make lines. Okay, now we want to look at what happens when it isn't a line and what is it when it actually represents something that's happening in a situation. Right? How do we interpret that graph? Okay, whether that's science class, whether we get into more complicated graphs, okay, we should be able to interpret a graph when it is given to us. Okay, so we're looking at graphs and how we maybe read and or interpret them. Okay, so how many of you say like in science class or yeah, math class. I'm trying to think of when else. Mostly in science. That's the one that I can just jump to right away. You have done something in science class and you have represented that information on a graph.
Yes.
We've done that?
Yeah.
Right? Okay, and probably in science class your teacher is giving you some vocab. For example, like when you make that graph, what are some things that your teacher has you put on the graph?
The two, like...
Okay, so we need some labels.
The label.
Right? Have we been given a specific word in science class as to what we call what we put down here?
Oh, independent.
Yeah, there we go.
And dependent variable.
Uh-huh. So our x, our input, is always our independent variable. What is the independent variable? Other than it's the x value or the input value. How do we decide what the independent variable is? Do we know? Okay, so the independent variable is the one that's either causing the other one to change. It's usually the one we can't control. Okay, if you don't know what else to put for the independent variable, the majority of the time, especially in math, we're looking at time. I mean, it doesn't matter what we do, we can't change time. Time is moving. Okay, and then you all just said it right. This is our dependent variable. Why am I not spelling today? Dependent. Ugh. Okay, and this is the one that we can change. I can control how fast I walk. I can control how much water there is. Now, sometimes when we say control, it doesn't necessarily mean that when you're doing a science experiment, right, you shouldn't like try and manipulate the outcome, right? So it's the one that is affecting the other. So were you all just doing like your marble things recently, right? And sort of the weight of that marble was being affected by how it went down that ramp or whatever? Wait, we're not controlling the weight of that marble, but we could change it, right? Okay, then three things can sort of happen in our graph. Our graph can go up. Our graph can be horizontal. Or our graph can go down. Now, whether it goes up in a straight line or up in a curve, or down in a curve, or whatever, right? It can go up, it can go down, and it can go straight across. And there are three words that we can associate with this. Okay? This does not mean uphill. So don't attach that in your brain. This gets assigned increasing. So what is this one going to get assigned? Decreasing. What is this going to get assigned? Oh, I love that word. Constant. And it is always per whatever the dependent variable is. Increasing, so let's say maybe this is speed. Increasing speed, constant speed, decreasing speed. Okay, so all of the green stuff always gets followed up with a label of the dependent variable. There's one other important thing that we need. I guess I'll do it in green as well since we're taking the same thing. Anywhere that we touch the x-axis, I don't know, I'm trying not to make another graph in here, but those are like when it's 0. Okay, when the dependent variable is 0. Okay, here and here, if we're touching the x-axis, the dependent variable is 0. And usually at this point, my students are like, sweet, awesome, I know all of this stuff, easy, got it. Right, we've probably all heard these types of things before. We feel okay with that? Okay. Oh, do you want me to go back? Now, obviously, our dependent variable can be labeled a variety of things. Height, speed, distance, number of potato chips you ate, total cookies, right? It can be kind of anything random, right? But there are sort of two very specific situations that can happen that are important in how we read a graph. One of them is just a specific label of the dependent variable, which is not a total. One of them is where it is a total. Okay, and I'm sort of leaving it as not a total and a total because the rest of the label doesn't matter. Maybe I say distance from home. That does not have the word total in it, so it would be not a total. Total distance walked. That has the word total in it, so it is a total. Does that make sense? When we were in total story problems, what was our format that we used? Blank plus blank, right? We added stuff up. So keep that in mind. That's still going to come into play today, okay? So now you get to watch Mrs. McKinney be kind of goofy. So, top graph, not a total. We're going to talk about my distance from the door. Okay? So I start walking away from the door. What happens to my distance away from the door? It's increasing, right? So whenever we're increasing, how do we show that in a graph? We go up. So if I'm representing my distance from the door, I started at the door. So I was 0 from the door. Okay, so I'm starting here and my distance goes up. Oh geez, that was a terrible one. Let's try that again. Okay, so now I'm going to stand here for a little bit. So now what's happening? It's a constant.
Is the bottom basically how long it's taking?
Time, yep, so this one would be time. Because if we don't know what it is, we should pick time. Doesn't have to be, but that just happens to be what we're doing right now. Okay, so I'm standing here, so now I'm going to turn around, and now I'm going to walk back to the door.
Decrease.
Okay, so decreasing, but am I just going to do this?
No, because you ran fast, so you went that faster.
I went a lot faster. faster, right? So when I walked away from the door, right? Walking, 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 walking.
So
And then when I'm going back, I'm going faster. So what do I do with my line there?
is it kind of like straight but going down a little bit, or is it straight now?
It's steeper. Okay? So it's important that we understand speed can be represented even if we're not talking about speed. It's represented in how steep we make the line. Now, one thing to avoid, this is a bad habit my students sometimes get into. They're like, oh, we went really fast, we did this. What's wrong with this?
That's just like
That's teleportation. Right? You're in two places like instantly at the same time. Yeah, not possible. Okay, so we can't do that. Okay, are we okay there? Okay, so now I'm going to do the same thing. I'm going to start over here, but now I'm going to do a total. So now I'm going to do my total distance walked. How do I know that it's a total? Because I literally have total in the label. Okay, so I start walking. Okay, what's happening right now to my distance walked? It's increasing. So how do we represent increasing? I'm going up.
Slope. Could you represent as a positive slope or no?
I mean, we can say that it's a positive slope, but we want to use the word increasing total distance walked.
Okay.
We are sticking to increasing, constant, and decreasing. Those are our three words that we can be guaranteed. And I'll give you an example of that in just a minute. Okay, so now I'm going to hang out here for a little bit. So now what's happening? I'm a constant. So constants are horizontal lines. And now I'm going back to the door.
It's going to increase, but it's going to be a little bit steeper.
Ah, so it's going to increase, but steeper. Why am I increasing?
Because you're still going at a distance. It's just faster.
It's a total distance. We add things up. So let's count the distance I've walked. 1 step, 2 step, 3 step, 4 step, 5 step, 6 step, 7 step, 7, 7, 7, 7, 7, 7, 7, 7, 7, 7, 8, 9, 10, 11, 12, 13. Does it matter that I turned around? No, I can't undo a distance that I've walked. So when we are looking at a total story problem, we can't decrease. Now, I'm kind of careful with this. This comes with a disclaimer because students will go, well, something can have a half-life and a chemical can decrease because in science the chemical evaporates. Or okay, yes. But I'm actually talking about a total where you're adding things together. Okay? Are we okay there? We say these things make sense. Okay, then that's all I need you to write down in your notes.